Hey, hey guys. Let's go ahead and do this here video, which is a fun lesson, and I think it's a lesson that we've already kind of seen a little bit of in the past. So I don't think it's anything too new. It's just now we're kind of summarizing a lot of the stuff that we've kind of covered and hit as we've gone through our last lessons. Okay. The lesson's called How Derivatives Affect Our Graphs. Basically, it's just how we can understand what our original graph looks like based off the properties of our first derivative and our second derivative. Okay? So let's read through these notes together. I'm going to try to keep it as short as I can, but you know how I am. Okay. Many of the applications of calculus depend on our ability to deduce facts about a function f from information concerning its derivatives. Okay? So we have different theorems and different tests that we can check as we go through describing our function. So the first one, okay, increasing and decreasing test based off of the first derivative. And we should understand this. We've talked about this in the past. But if f prime is greater than 0 on some interval, we'll think about what that means. Greater than 0. And that means f is increasing on the interval because it has a positive slope. Same thing here. If f prime is less than 0 on some interval, then f is decreasing on that interval, which again should make sense because that's when your slope is negative. You're decreasing and going down. Let's look at an example. Find where the function x to the fourth minus 6x squared is increasing and where it is decreasing. Okay, increasing and decreasing. So where the slope basically is positive and negative. I think a good first place to start is to find critical points. Alright, find where it's doing neither increasing or decreasing. Okay, that's what happens at a critical point. That's where we have a max or min. So we're going to let 0 equal our derivative of the function, which is 4x cubed minus 12x. And just doing some simple algebra, we can solve 0 equals 4x, x squared minus 3. All right, and then setting each one equal to 0, we got that x equals 0 and x equals plus or minus square root of 3. So those points right there, those are our critical points. All right, if I want to know where my increasing and decreasing intervals are at, check our sine line. Okay, so what I mean, we're going to check intervals on the sine line. So make your little number line. Put your critical points on the number line. So we got square root of 3, we got 0, I'm sorry, negative square root of 3, 0, and positive square root of 3. That's when it's neither decreasing or increasing, neither one. So let's check the intervals to the left and right of that. So plugging values into our derivative function, all right, if I plug in, say, negative 5 or negative 10 or something like that, we'll have some negative value times some positive value, so it would be negative right here. Say I plug in a value between negative square root of 3 and 0, say negative 1. Well, that would be a negative times a negative, which is positive. If I plug in positive 1, that would be, again, a positive number times a negative number, so that's negative. If I plug in, say, 5 or 10 or anything bigger than square root of 3, it's going to be a positive times a positive, which is positive. So there's our intervals on our sine lines when our derivative is either negative or positive. Where it's positive is where my original function is increasing. Where it's negative is where my original function was decreasing. So let's summarize that real fast. So f is increasing when f prime of x is greater than 0. All right, and that occurred at negative square root of 3 to 0, and from square root of 3 onto infinity. All right, f is decreasing when f prime of x is less than 0. And we determined that occurred at negative infinity to negative square root of 3 and 0 to the square root of 3. All right, good. Any questions? Great. So that's using the derivative to determine whether our graph is increasing or decreasing. Let's look at some more things our derivative can tell us about the original graph. If f has a local maximum or minimum at c, then c must be a critical number. We talked about that a couple days ago. Of f, but not every critical number indicates a maximum or minimum. The following test will tell us whether or not f has a local minimum or maximum at a critical number. It's called the first derivative test. So suppose that c is a critical number of a continuous function f, some critical number that we have found by setting the derivative equal to 0. If f prime changes from positive to negative at c, then f has a local maximum at c. Think about that. If I have some number c, if it goes from being positive to negative on my sign line, that means that I'm going from a positive slope to a negative slope. That can only occur at a maximum. Same thing for number 2. If f changes from negative to positive at c, negative to positive, then it has a local minimum. Think about it again. If I had c on some number line, and to the left of it, it makes it negative in my derivative, it makes it positive in my derivative, that means that I have a negative slope going to a positive slope. That indicates that we have a minimum. But if f prime does not change signs at c, for example, if f prime is positive on the left and positive on the right, or negative on both sides, then f has no local maximum or minimum. Okay? So the sign line will look something like this. Here's our critical point. We would have a positive slope on one side of it and a positive slope on the other side. So in this case, we would have no max and no min. So the first derivative test allows us to decide if we have a maximum value or a minimum value at c. So let's look at the example that we did earlier. Okay, we had already done this example instead of equal to 0. So if I'm trying to find where I have a local minimum and a local maximum, I'm trying to test those critical points. Okay, so if you remember when we did this problem, we had 4x cubed minus 12x equals 0, or 4x times x squared minus 3 equals 0. And we determined that our critical points were 0 and plus or minus square root of 3. Okay, so again, let's look at that sign line that we had earlier. Okay, so we had the negative square root of 3, we had 0, we had positive square root of 3. And doing some test points, remember that we had negative, positive, negative, positive. Okay, so let's think back to what our rule says for the first derivative test. Here we have a negative slope going to a positive slope. Then we have it going to a negative slope and a positive slope. Okay, because the signs change, we do have local max and mins at these points. Okay, and I think drawing these slopes can help you easily see what kind you have. So at negative square root of 3 and positive square root of 3, we have a local minimum. Okay, because our y values or our slopes are going from negative to positive for both of those. And at 0, we have a local max because our rates or our slopes are going from positive to negative. It makes that hump, it makes that shape. It is asking us for the values though. So if I want to know for the max, okay, I'm going to plug negative square root of 3 in for x. I'm sorry, this is for the not maximum, this is for minimum. So if I wanted to know the minimums, I could plug negative square root of 3 in for x, okay, and the value I get, that would be my minimum value. You plug negative square root of 3 in, you get negative 9, which is the same thing if you were to plug in the positive square root. Okay. So that's our minimum value. Our maximum value is when we plug 0 into that. So our max would be when I do f of 0, which ends up being 0. Okay, looking at the next example. We are trying to find the local max and local minimums between the intervals 0 to 2 pi of this function. Okay? So first we need to identify the critical points. So start by finding g prime of x, which ends up being 1 plus 2 cosine of x. Then set that equal to 0 to identify our critical points. And solving this real quick, we got the cosine of x equals negative 1/2. And this occurs where x is equal to 2 pi over 3 and 4 pi over 3. All right, between the intervals 0 and 2 pi. So those are the points we're going to check on our little sine line over here. And we are looking between 0 and 2 pi over 3 and 4 pi over 3 and 2 pi. So test some points. Test some points between these that you know you can take the cosine of, like maybe test pi over 3 here. A point between these two would be pi. Maybe try the value, I don't know, 5 pi over 3. All right, putting those into our equations, and you can test them yourself. I'm getting that this is a positive number, a negative number, and a positive number. Okay. So that means that we have a positive slope here, a negative slope here, and then going to a positive slope over here. So that's kind of what my original graph is looking like. And that should make sense with a cosine function. We do normally have some curve-like features. Okay, so it's going up and down, up and down. So that means at pi over 2 we have a maximum, or 2 pi over 3 you have a maximum, and at 4 pi over 3 we have a minimum. So let's write that down. We have a local minimum at 4 pi over 3 and a local maximum at 2 pi over 3. If I wanted to obtain the actual values that it's asking for in this problem, you would plug those back into your original function. And plugging those, back into our function, our original function, we get that, just an unsimplified version, we have a maximum at 2 pi over 3 plus square root of 3. And we have a local minimum at 4 pi over 3 minus square root of 3. Okay. So there's your answer. We were able to find the max and min using our derivative only. Okay, so that's what the first derivative is helpful for. It's helpful for finding the intervals in which your function is increasing and decreasing, and also helping you identify what your max and min values are. All right, the next couple that we're going to be talking about is what your second derivative is useful for in describing your original graph. So, if the graph of f lies above all of its tangents on the interval I, then it is called concave upward. And we should know what that shape looks like. I'm about to draw in a second. But if the graph of f lies below all of its tangents on I, it is called concave downward. All right, so here is concave up. All right, this means that our function looks like it is almost a smiley face, if you want to think of it that way. But every single tangent line that I were to draw, my graph is going to lie above it. Okay, this is concave up. Concave down is the reverse. All of the tangent lines on this graph are going to lie below it. Okay? And a second derivative helps us identify when our graph is concave up versus concave down using the concavity test. Okay? So, it states that if the second derivative is greater than 0 for all x in the interval I, then the graphs of f are concave up. If the second derivative is less than 0, then our graph is concave down. So let's look at some examples of that. One thing I want to say though, the point at which a graph changes from concave up to concave down is called an inflection point. Okay, so maybe make a note somewhere that first derivative equaling 0, that is a critical point. Okay, whenever the second derivative of x equals 0, then we have an inflection point. So critical points go with first derivative, inflection points go with second derivative. Okay, the function must be continuous at that point though. Okay, there is a point of inflection at any point where the second derivative changes signs. Okay, so wherever the second derivative equals 0. All right, so if I were to say I had a number line, okay, and I'm looking at my second derivative, if this is the value c where it's at 0, that is an inflection point. I would have maybe negative to the right, positive to the, or negative to the left, positive to the right. This would be concave down, this would be concave up, and this right here is the point of inflection. That's the point where it changes concavity. Let me show an example right below it. Here we have our graph. It could look something like this. So here we're concave down, and then at the inflection point we change to concave up. This is our inflection point, where our graph goes from being a negative concavity to a positive concavity. This inflection point. It's a terrible drawing, but it's just where my f double prime of x is equal to 0. Okay, let's do this really awesome example. That kind of example 5 that kind of brings all this stuff that we talked about with concavity and inflection points and increasing and decreasing max and min, everything to do with the first and second derivative. Okay, so it says, sketch a possible graph of the function f that satisfies the following conditions. Obviously, the answers can vary, but let's kind of come up with one together. The first part here, I, it says that f of 0, as well as f prime of 2, f prime of 0, f prime of 4, and f prime of 6 equals 0. So from that, we got the point f of 0 is 0. So we got the point 0, 0 is going to be on the graph. But more importantly, look at every other number we got. It says all of these values plugged into the derivative is 0. Remember, those are critical points. And when our functions have critical points equaling 0, that's where our local max and mins kind of occur. Okay? So let's just kind of summarize that on a number line here, just so we kind of have that information available and as we're looking at when we're graphing. Okay? So it says that at, let's see, in order 0, 2, 4, and 6, we have critical points. Let's keep that in mind as we look at the second point here. It says f prime of x is greater than 0, so is positive for any value between 0 and 2, so I can put a plus here. Or between 4 and 6, so I can put a plus here. All right, so then that must mean that on the other sides, then it's going to have to be negative. And we'll show why this is negative here in a second. Look at f double prime of x. Okay, it's saying that f double prime of x is greater than 0 when we're between 0 and 1, or when we're between 3 and 5. And it's also telling us that it's less than 0 between 1 and 3, and when we're greater than 5. Let's draw that on a number line as well. And I like to keep it as consistent as I can with this one right here. So we're talking about between 0 and here's 1, and between 3, which is right here, and 5, which is in between here. Okay, so let's write down what it says. F double prime is greater than 0 between 0 and 1. So that means we have a positive value here between 0 and 1. Or one between 3 and 5. All right, and then the second bullet, or the last bullet point, it says that it's less than 0 when between 1 and 3, so that's negative, and when between, or greater than 5. Now, if you're going to look at this, if we're going from negative concavity to positive concavity, okay, the only way that can happen is if our slope is negative. So that's also another way, or another reason I can assume that between 2 and 4 we have a negative slope. Okay, so look, we have some information about our graph between the points 2 or 0 to 6. But something else I want to notice, this right here, f negative x equals f of x. If we think back to a few classes ago, maybe it was pre-cal, geometry, I don't know. This is telling me that we are symmetric about the y-axis. Okay, so it's a reflection across this line right there. Okay, that's what that transformation is telling us. So whenever I plot between 0 and 6, I can transform to the left side of the graph as well. It's an even function. All right, so let's kind of take these points, all right, and try to create a graph based off them. I'm going to start by graphing my critical points. So 0, 0 was given to us. We don't have a y value for 2 or 4 or 6. So I'm just going to kind of randomly give some points. Maybe at 2, let's write, we'll plot here. At 4, we'll plot here. At 6, we'll plot, I don't know, here. Okay? And again, this is just a possible sketch. We don't know the y values that go with that. There's no way to tell. But I do know that these points are going to be extremely. Okay? Now, I know that I'm going to have a positive slope between 0 and 2, a negative slope between 2 and 4, and a positive slope between 4 and 6. So I did have to have this point greater than this point, and this point greater than this point. That's the only way to ensure that I keep that positive and negative slope. It has to be able to have a positive slope and a negative slope between those points. Here would be positive, here would be negative, and positive. But I got to be careful because of what the concavity is. So between 0 and 1, it's concave up. So it's like a smiley face. So it's almost like I'm curving up like this. But then from 1 to 3, I'm making a frowny face. I got to hump down. But then from 3 to 5, okay, I'm doing another smiley face, so I'm going up. But then it starts to do a, I guess, what's the word I'm looking for? A frowny face again. So here it's concave up, switches to concave down. Then when we get to this point, it concaves up and then back down. Okay, the concavity kind of comes with practice. But at, let's see, at 1 is where it changes concavity. At 3 is when I'm trying to change concavity. And at 5, it's changing concavity again. So here's concave up, concave down, concave up, concave down. And there's a pretty good drawing of the graph. The only other part we got to do is talk about the symmetrical part, about the y-axis. So let's just transfer those points over. What did I say? 2, 3, so negative 2, 3, 4, 1, negative 4, 1, or 6, 6, or negative 6, 6. We'll try to draw that same shape if I could. Maybe not as good, but there you go. There's a sketch of the graph using what we know about the first and second derivative. I think that is awesome. Okay, the last thing I want to talk about today is the second derivative test. We talked about the first derivative test. The second derivative test also has to deal with the local maximum and local minimum. But that's kind of combining what we know about the first derivative and the second derivative. Okay, this can be helpful when we have the second derivative, or we don't want to use the first derivative test. And we'll talk about the different possible cases when that would happen later. But for now, what it's saying is if we know that f prime of c is 0, so if we have a critical point, and I also know the value of c in the second derivative is greater than 0, then I have a local minimum. I'll talk about why that is in a second. If f prime of c is equal to 0, if we have a critical point, but the second derivative is less than 0, then we have a local maximum. All right, think about what I'm saying. All right, we have c as a critical point. All right, if it's concave down at this point, so it looks like this, that's the only way that we can have a minimum and it be concave down. All right, same thing for this one. If we have a c value and its derivative is 0, it means we have a horizontal tangent line, then it's concave up, and we have a local maximum. I just realized that I switched those. So take my argument and just flip-flop this. This is where we have f double prime of c is concave up, so this would be here. This is when f double prime is less than 0, concave down, we'd have a local maximum. Apologize for doing that. It's a long video. But anyway, as long as you get everything up to the graph of the previous slide, I'm happy. We're going to do more of this tomorrow. So yes, switch that. Apologize. This is concave up. All right, it's greater than 0, so we have a local minimum. This is concave down, so we have a local maximum. Okay, this prevents us from having to do the number line with the first derivative test. Okay, so let's look at this example. Discuss the curve 3x to the fifth minus 5x cubed plus 3 with respect to concavity, points of inflections, and local max and minimum. Use this information to sketch the curve. All right. In order to talk about concavity, points of inflections, critical points, we need to find the first derivative and the second derivative and set each equal to 0 so we can compare. So let's first do f prime of x equals 15x to the fourth minus 15x squared. So solving this, we got 0 equals 15x squared, x squared minus 1, or x equals 0, x equals 1, and x equals negative 1. All right, those are our critical points. Now let's find where f double prime is equal to 0. Those will be considered our points of inflections. And then we can compare and sketch based off of that. So f double prime of x equals 60x cubed minus 30x. Solving for this, we have 30x 2x squared minus 1, x equals 0, x equals plus or minus the square root of 1/2. All right? So here we have critical points. Here we have inflection points. Okay? Now, let's kind of compare this on our number line. Let's look at these values on a number line. Here's f prime, here's f double prime. I'm just kind of plotting these in the best order that I can. We're looking at -1, 0, and let's see, what was the other one? 1. And our points of inflections were 0 again, and negative square root of 1/2, which is like right here, and positive square root of 1/2, which is like right here. All right, kind of using the second derivative test, plugging in values in between these numbers on the second derivative on f double prime, we get that the second derivative is negative, positive, negative, and positive. Okay? So I'm saying that this is concave down, this is concave up, this is concave down, and concave up. If, based off of the second derivative test, I can assume that because my second derivative is negative at my critical point, -1, but that must mean that this has to be a maximum. If the values are equal to each other, 0 and 0, okay, that just means 0 is a point of inflection, okay, neither a max nor a min. And here, at 1, since it's concave up, it's positive, that has to be a minimum. Okay, so we have a maximum at -1, we have a point of inflection at 0, we have a minimum at 1, and we also have some other points of inflection, negative, square root of 1/2, positive square root of 1/2. Let's kind of sketch that based off of that information. So, plug in my critical points back into my original function at -1, which is like right here. It ends up giving me the value 5, so 1, 2, 3, 4, 5. Plugging 0 into the function, I end up actually getting 3, which is right here. And plugging 1 into the function, I end up actually getting 1. Okay, so I'm just plotting my critical points here. Now, using what I know about my points of inflection, so I know it's concave down, and at negative square root of 1/2, it's changing concavity. It's going from negative, so here we have a negative concavity. Then it's going to shift to a positive concavity. All right, but what I'm saying right here at this point of inflection 0 is now that it's going to be changing from a negative concavity to a positive concavity. And then when we get to positive square root of 1/2, it's going to change concavity again and become a positive concavity. And that's what my function roughly looks like. And we're going to get better at that, okay? We're going to get really good at that. We're going to learn how to graph our critical points, when to know when it's a maximum, a minimum, a point of inflection, how to change concavity. It's all leading up to curve sketching, and we're going to practice this again tomorrow. So hopefully, at least up until we had to start sketching, hopefully it all made sense. Thank you for bearing with this video and watching it. This is your homework for tonight. And we will answer any questions that you have tomorrow and pick up this tomorrow when I do a little activity. So good luck. I love you guys. Glad that video's over. No 5 points. Don't try me this time. Never know how to end these things. So yeah. I think I covered everything. Feeling kind of happy. Hopefully you're not too scared. Okay, bye. Seriously.